this lecture already of Intro to FEA. So I believe you've been warned that you would see me here today. So it's my great pleasure to be here and work on the first extension of your finite element repertoire in this lecture today, where we will go one step further and we'll start accounting for beam bending. So today we'll cover the theory, and on Wednesday we'll start implementing this. But before we go ahead and start extending our repertoire, let's quickly recap the general strategy and what you've been seeing in the last week when we were finally introduced to the finite element method. So in general, what we want to do is, I know you've seen this projector many times, right? For example, this is always a nice example to show. So we have this projector suspended from the ceiling, and we would like to know what is the displacement field inside here. And ideally, right, we would like to do this via a numerical method. So the first step we have to do is already making a bunch of assumptions to come up with a mathematical model to describe this exact rod hanging from the ceiling with this projector at the bottom. And these assumptions that we make here are that this is a long and slender rod that our projector is hanging of. We presume it's made of homogeneous material in this case. We say it's fixed at the top, and the projector at the bottom will just model as a force applied at the end. Then we have our unknown equation, our unknown field here, which are our displacements, our u's. And I think I'm not in the PowerPoint, and it's not recognizing my pointer. Anyways, so we have our displacement field u, this is what we want to solve for. And for this we can write out the governing equations, right, using Newton's second law, as you've been already learning in your mechanics courses, what you see down here, plus some boundary conditions, and we have the governing equations defined, and we could start solving this problem. Now the issue is, if we want to solve this numerically, if we want to use a computer to solve this, we can't just throw this at a computer, right? A computer, what we can do is solve for discrete values, we can solve for a linear system of equations. So we have to go one step further to define our numerical model. And this is exactly what you've been seeing last week for this rod, where we looked at bar elements, we introduced finite elements, so discrete values that we're now solving for, other than this continuous field u of x. And we said the crucial point that we made here was to introduce an ansatz for this continuous displacement field, which we call UH. And here we introduce shape functions, so that we still have a continuous function along the beam, but with distinct values at each node that we'll be solving for. Right, so here we have a vector of unknowns, and then you saw how you could formulate this as a system ku equals f, and this we saw already in lab 1 and 2. This is something you can throw Python, C++, wherever, a linear system you can solve using a computer. So once we've solved for this, we can then compute the solution, and we can use this to compute a bunch of different quantities. For example, here we could take a look at the stress in the system. Right, for this example, it might be a bit trivial, but later on when you start looking at complex geometries and so on, you might really want to know what is exactly the stress state at all points. In this case, would I have designed my rod strong enough to hold this projector? And this is what we'll be looking at today. Yeah, so this is typically what we're doing, and we're now doing this, and really what we'll be focusing on in the next few weeks is at these ansatz functions down here, defining different elements, different ways to compute a numerical solution. One point I want to make now, which you'll get back to later in the course, is of course you always have to check that your solution does make sense. Does this actually portray physical reality? This is something you might be able to do through experiments, or typically that is what one does. So experiments or some way to verify that this pretty colorful picture you see in the end, that this is actually the solution that we're seeking for. This is actually showing physical reality with some assumptions, but that it is actually correct. But that you'll get to later in the course, how we can do this. So as I said, let's quickly review the finite element method. You saw that you could derive this, the weak form in class last week, where you come exactly to this conclusion that you have a system ku equals f. And the important thing here was that you had these shape functions that you could plug in, and like this you could define k, you could define f, because these are all known values you have in here, and solve for u. And you have discrete values, and as I said, the starting point are these shape functions which define different elements, so that you get a smooth solution in the end. These shape functions we saw were piecewise polynomials, right? That's what we'll see in this course, or in general in the finite element method. And they had a very important property, namely this Kronecker delta property, which means we have local shape functions, and it means nothing else that each shape function is associated to one node. So n has to take up 1 at this node, 0 everywhere else. You will see this later in 2D, always this condition has to hold. If there are any questions, like always, please raise your hand and we can discuss. So this was one crucial point of these ansatz functions, of these finite element interpolation functions, the shape functions that we saw. For the bar element, you saw this last week, you derived this in class. You saw we had two nodes, you could define two linear shape functions, right? One at one node, 0 at the other, and you had the displacement field described like this. And from this, of course, you can then also compute the strains, which we saw were constant in this case. You quickly touched upon it that we could also introduce more nodes in our bar, right? Instead of 2 nodes, we could have 3 and have a quadratic shape function, for example. And you saw that this was done by special polynomials called Lagrange polynomials, which are defined as such, which I think we'll be seeing in your stack questions as well. This sounds so far so good to recap, hopefully, of what you saw. So this is, again, repeating once more. So you have u1 times n1, u2 plus n2, u3 times n3, and so on, to then in the end come up with your, let's bring this guy across, with your displacement field over here, which is piecewise linear, because this is what we chose as our shape functions. Right, you remember you had a u comma x, delta u comma x in your weak form, hence we needed at least piecewise linear functions, because we needed a first derivative. Then we said, how could you make this more accurate? You had a few strategies that you discussed here. One, of course, being having smaller and smaller elements. Then this piecewise function would also start looking more smooth, that you see on the side here. As I said, you could have higher order polynomials. You could have higher order polynomials and make your elements smaller. And another strategy that's often employed is this R refinement, where you see where do you expect high stresses or strains, and there you might want to refine. So introduce many more nodes in this region while having a coarser mesh without. And this is how quadratic shape functions look like in this 3-node bar. You saw this in class last week. So one more point that I want to mention before we move on, using defining shape functions in this way has another really great advantage, right? Is we can impose our boundary conditions very easily, right? Because we have n1, u1, we can define each point where we have a boundary condition, we can directly define it, which makes our life a lot easier. But now we'll start looking at something a bit more intriguing than the 2-node bar element, looking at beam bending, and here's an example of how you can think about this. So we had pin-jointed trusses, right? That's what we've been coding in lab 2. So these would only stretch or compress, and they were pin-jointed, which means, right, they can rotate here. So the angle can change as you were to load it or pull on the sides. Whereas now what happens if we weld this joint up here, right? Then all of a sudden when we pull on it, this angle can no longer change. And this is typically how we define beam bending, right? Because now these trusses won't only stretch anymore, but they will have to bend to account for this rigid joint at the top. And this is exactly what we'll be looking at today. So again, something close to home. I mentioned these architected materials a few times that we look at in our lab. And down here, for example, you see this octet type structure where you see at one node there are only 3 bars connected, or 3 beams in this case connected, and if those were hinged, this structure would just collapse, right? So you actually have to model this as being rigidly welded at the nodes, otherwise it couldn't hold, whereas stretching dominated structures could be pin jointed easily. All right, so with this, let's start looking at these beam elements. Let's start deriving this beam finite element in class today, and we'll also chat briefly already about it, how we will be able to incorporate this in our lab in project 3. Any questions at this point? All right, then let's move over to the board wrong. And how do we, I hope this is light enough. All right, I hope this is light enough that everyone can see nicely. Now let's start on this front board. All right, so all of this you can find in chapter 12 of the lecture notes, called beam elements. And what we'll start with today is hopefully going to be nice and easy for you. In theory, you should know these beams from your mechanical solids classes. At ETH, that's mechanical. Next two. So hopefully you have some aha moments, and this looks quite familiar what we do in the first little bit here. So let's start with a quick refresher of beam theory. Right, we were interested in pure bending in our case. Let me see, this is the correct board. Ha. All right. So yeah, maybe let's start by defining our axis X, which runs through the middle of our beam, through the center of our beam. Beam's a bit short and stubby, but that's okay. And what we'll do differently here, so you already see I call this X. We'll be using a slightly different coordinate system here just because this is how you would have learned it in mechanics too. This is typically how you would see it, that you have X, the X coordinate running along this over here, which is called your neutral axis. Right, this is meant to go through the center of the beam. And then over here we have our Z coordinate pointing down, and hence your Y coordinate coming out of the board. This should look hopefully familiar to you. And then what we'll do is we'll look at what happens when this beam deflects. Drawn beautifully here. So here again, I would have done something similar to what we've done in our coding lab so far. This has a scaling factor of like 500 on it, right? Because we are dealing with something like a steel I-beam or rectangular beam in this case. So the displacements are very, very small, right? Small angles, small displacements, and we're just exaggerating this so that we can see nicely. And then what we'll do, we can look, for example, what happened to this point here. And we define that it went straight down here by W of X, which we call our deflection, right? So deflection is, in German you would know it as the Biegelinie of your beam. And then we introduce one more thing, which is this went straight down, but we also say our beam rotated. So let's draw this in like this. So we say our beam also rotated by psi of X, and this is the orientation. So far, so good. Some looks very familiar, I hope, or at least awaken some memories in some of you. All right. So we said we're assuming small displacements. Small displacements, right? Because it's a linear elastic beam, small angle, small deflections. This is highly, highly exaggerated what we see over here. So let's write out our displacement field U of X. And this is nothing else. Let's start at the bottom. In the Z direction, right? We said our beam simply goes down by X, right? So this would be W of X. In the Y direction, there's nothing happening, right? Our beam is bending in plane. So we can call this 0. And then what is our displacement in X direction over here? And this is maybe easier if I draw it here. So for example, we want to know what happened to this beam, and after it, because we say it goes straight down, and there's the rotation over here. So because this is a very, very tiny displacement, right? Very tiny angle, very tiny rotation. As what can I write this? Yes. Exactly. So we could write that as simply minus psi of X multiplied by Z, right? This little bit over here, the minus sign being we're moving in the positive X direction when we're moving in negative Z. All right. Look familiar? Great. So we have this nice thing over here, but it's still a bit frustrating, right? We have two variables which define our entire deformation. I mean, that's great and so on, but it will make our life a bit difficult to solve. So, wrong board. So let's go ahead and do one more assumption, which you should hopefully also remember well. And that is, let's take a look at an Euler-Bernoulli assumption. And Euler and Bernoulli were in fact both Swiss mathematicians, in case you didn't know. And this assumption here, also this is again a recap for you. Here we assume that beams are long and slender. Long and slender. And because our beams are long and slender, we can say that our cross sections remains perpendicular to our neutral axis. And by making this assumption, right, so this beam is very thin, and in other words, this means this angle over here, right, that's 90 degrees, and here, this angle will also remain 90 degrees, but yes, between our cross-section, our neutral axis, this will remain at 90 degrees, which means when we rotate our beam down here, right, when we go from our horizontal axis rotating down here, this angle would then also be psi. Of x. So seeing that we're using small angles and making this Euler-Bernoulli assumption, what can we now approximate psi of x as? If you're thinking of this over there. Right, if this angle here is also psi of x. You should hopefully remember this also from your beam class, right? You have small angles, so sine psi is the same as psi. Does anyone remember what this is? Or can see what this is? Right. Yes. Exactly. This is then nothing else but w comma x, right? dw dx over here, the small angle. You can take your arctan of psi would simply be psi, and then you have your little dw dx. So you can, this is the main assumption you would make here, which is great, right? Wrong board. Can you still see? So this assumption is really nice now, because then when we substitute our psi of x over here with w comma x of x, of course, now our displacement field looks a bit different, right? One day I'll get it right to push the correct button. So here we can now write out u simply being as minus w comma x of x multiplied by z, 0, and here we have w of x. Right, so far so good, I hope. Yeah, otherwise please ask. And now let's go ahead and do what you've been doing all along. Let's write out our strain tensor, in this case, right, we're in 3D. So let's write this out. First entry over here, right, that's u1, this guy up here, taking the derivative with respect to x. So here we would simply have minus w comma x multiplied by z, right? Epsilon 2, 2, right, that would simply be 0, right? u2 derived by y is 0. And then we have w of x here at the end, derived with respect to z, will also give us 0. Our cross, this guy over here, right, that would be a half times u1 derived by y, 0, plus u2 derived by x, also 0. Well, wait, wrong guy I was looking at. No, I was looking at this one. And this one here. And then this guy over here, what is this value? So here we have these two combined, right? We would say this derived with respect to z plus this derived with respect to x multiplied by half, right? So we would have here this derived with respect to z would be minus w comma x plus this derived with respect to x is w comma x. So minus plus would cancel, right? And we have a 0, and the whole thing multiplied by a half. So what we see is in pure bending, we only have this one strain value at the front here. Maybe this will now make more sense to you. So if we now write out our strain tensor over here, right, and we're in the linear elastic case, right? That's what we said. We're dealing linear elasticity, small strains, small angles, small deformations. So we could simply use Hooke's law, which is sigma multiplied by E multiplied, right? Young's modulus multiplied by now W comma XX, Z, and everything else is 0. And here, if we quickly draw a cross-section of the beam, right, here we have the end of our beam. Here we have X coming along, Z is pointing down. If you were to draw this in, right, we see it varies linearly in Z. So it would look something like this. Right, this would be your sigma XX if you draw it. And this makes sense. Do you know where the pointy stick is usually kept? This side. Thank you. Right, because when we start bending a beam, right, at the top it's in tension, and at the bottom it will be in compression, right? So this makes a lot of sense what we're getting out here, and this is the only deformation mode we see in beam bending. All right, so far so good. Okay. Then let's move on, because I promised you we would be looking at finite elements now. So let's do our first step towards moving towards finite elements. And remember there you needed a strong form, a weak form, so we had to understand our problem. And then we needed a strong form and a weak form and so on. So the first step you may have done there is to write out the stored. Let's bring this a bit further down, too short. Write down the stored elastic energy in our beam. Oh, energy, sorry, elastic energy. In our beam, in bending. In pure bending, as we were discussing here, and you saw, well, this will be a functional, right? And it will take in our deflection W, as this is now a governing variable that we need to solve for in our system. And we know, you've seen this in class before, this will be over the domain. You will have to take into account the elastic energy, which was nothing else but your sigma ij, epsilon ij, right? Your stresses, your strains, dV. So let's write this out for our beam over here, right? All we have to do is sub in, let's move this up so you can see it, right? Sub in our sigma ij, epsilon ij. It's very easy, seeing that we only have one value here at a time. So this is the same, basically looking, when you pull on a string or so, what's the energy stored inside? In this case, we're bending a beam and we're looking at what is the elastic energy that is now stored within this beam. So in this case, well, we said we have a beam, say it has length L. So we would have to integrate over the length of the beam, and we would also have to integrate over its cross-sectional area at each point, right? So when we now do this multiplication here, we have a half, right? We have this E over here, the minuses cancel, so I can write down E over 2 multiplied by W comma X squared, right? Z squared dA and dx, right? dA stemming from our integral over the area and dx over the length. And now let's rearrange this a little bit, right? So we can have our integral going from 0 to L. And let's pull out everything that does not actually depend on the area, on the x or y. So we know E, we assume to be constant, but also our W only depends on x, right? So we can pull it out of the area integral. So we have W squared comma x inside here. And then we're left with an integral over the area of Z squared dx. dA. And then of course we have dx closing this integral over here. What is this Z squared dA? Exactly. It's our area moment of inertia, right? We usually call this IY, and this is nothing else but our area moment. And our area moment tells us how much resistance against bending we have. So now if anyone has a ruler here, for example, if you were to keep it flat and try to bend it, it would be very easy, and if you turn it upright, right, and you try and bend it in this direction, it will be very hard. It's because your Z is further away from your neutral axis, hence bending is more difficult. So this is our area moment. Simply says how much resistance against bending we have. So then, let's write this out. Now we have our integral from 0 to L of E. We can take the IY forward, right, and we're bending about Y. This is why we have the IY over here, over 2, and let's be more consistent here, right? W just depends on x. This is squared dx. This is now the stored elastic energy inside our beam. Now, this over here, this looks quite similar to what you saw last week, doesn't it, to the bar elements? You remember you had something like a EA over 2 and a U comma x. So what's the main difference you see here? Yes, please. Exactly, we now require a second derivative. So this is really what's quite special about these beam elements, and let's go ahead and start writing out. Let's start writing out the variational formulation and coming up with our first actual finite element simulation for a beam. So actually I went a bit too tall here, didn't I? So let's write out the full variational formulation, which you find in chapter 12.3, variational formulation. And for this, let's consider a beam with the following boundary conditions. And here I must probably start taking some color into account. So let's draw this beam a little bit thinner than last time. We still have our x coordinate running along there. We'll have z coming down, and y will again come out of the board. Let's say this is of length L, and seeing that we want to derive a finite element, a beam element, let's say that our beam has 2 nodes, right? That's what we're aiming for in the end. We want a 2-node beam element that we define, nodes 1 and 2. And, can you see this color when I draw once? And then let's add some sort of distributed load here along the length of our beam. Call this Q of x, right? Just some distributed load that you might have along the length of your beam, like, I don't know, snow lying on there. And then let us introduce 2 forces, one acting on this side, which we'll call Fz at node 1, pointing down here. And over here, let's have another force pointing down, which we'll call Z at node 2. It's a thick piece of chalk. And finally, seeing that we're interested in beam bending, right, let's also introduce a moment. Sorry, this is node number 2. A moment at node 2. And then also, let's also apply a moment over here at node number 1. Right, so this is the beam that we are, this guy, that we'll be considering for now. And with this, let's write out our potential energy functional. And this will get a lot of writing, but let's go for it. So here now we want the functional, so we have I of W, right? Our total potential as a function of W, which is the energy inside the beam, which we wrote down up there. So that would simply be integrating from 0 to L of E I Y over 2 multiplied by W comma x of x squared dx. And now when we want to write out our potential energy functional, we also have to subtract from here the work done, right? So we would have minus, let's start with the distributed load. That we also have to integrate over the length of the beam. So we have minus the work done, integral from 0 to L of Q of x. And work done is 4 times displacement, so what has to go into here? Yes, exactly right. Q of x is working in our right w of x direction. So here we have our force times displacement is our work done, dx. And then we get to add all of our individual force terms over here. So we can add Fz1 multiplied by the displacement here, which would be w of 0. We have minus F2 of z. This one acts as at w equal to L. And then let's go into the next line here. Then, of course, we also have our moments. What do I multiply the moments by? Yes, please. Exactly, the moment multiplied by the angle. And the angle, we said, is nothing else but w comma x. The moment at node number 1, that would be then the angle at 0. And over here, we have the moment multiplied by the angle, right, comma x, et al. Is this completely correctly how I wrote down the moments here? Yes. Exactly, good point. So we subtract the work done on the system. So this is correct up here. But the moments, you're absolutely right. The moments and the rotations have to point into the same direction. So we actually have to add these contributions here as they go against the direction. Okay, fantastic. And then what you saw in classes, right? Once you have your potential energy functional, what you would like to do is minimize it with respect to w of x, right? That's our value that we have in here. Was this the correct one? And the way you learned how to do this with a potential energy, with this functional over here, is by doing something, taking the first variation, which essentially means you can think of taking the first derivative. It's similar, just that this time we have a function that we have inside here. So let's take the first variation, that's a delta I. That's how we note that it's a first variation, and this has to be equal to 0. And if we do this variation, we have here the integral of 0 to L. The 2 multiplies forward, cancels out this 2 over here, so we have E Iy multiplied by w comma xx. I'll drop that dependency on x there. And then we introduce our delta w over here, comma xx dx, right? And the same, you learned how to do this, I think, last week or even the week before. And then we can move on and do the same, take the first variation of all of these terms over here. So we have the integral from 0 to L over here of q, and this we simply can then multiply by dw dx, right? First variation of this term over here. And then the rest follows quite simply. We have minus F1 delta W at 0 minus F2 Z delta W at L. And then let me continue along the length here. We can say plus our M1Y, and that's then multiplied by our delta W at 0 plus our My at node 2 delta W at L. Right. And now you saw something very similar over here for our bars, right? Where you had a U comma X delta U comma X. Now we have a W comma XX delta W comma XX, and we would like to get rid of these comma X's XX on our delta W. So what do we do? Right. Integration by parts. This is very tedious to write out. So I will just give it to you. So we want to do integration by parts twice here, right? First time this X comes over here, and then we have a delta, then we have a surface term that comes up where we have W comma X X X delta W comma X evaluated at 0 and L. Then we do it again, so we have W comma X X X X and delta W coming out of there, and we have a surface term that pops out at 0 and L. So let's write this out down here. So after integration by parts, right, IVP, which we do twice, right, on this term over here, what we end with is that delta I is nothing else but the integral from 0 to L of EIY W comma X X X X, right, because we did integration integration by parts twice here to get the x's onto the w and get rid of them over here. And then we'll have a delta w dx, so let's combine these two terms over here and subtract q from it. And we multiply this by. So this would mean we would have w of 0 would be equal to some prescribed deflection at 0, at x equal to 0. And then we can do the same thing for the rest of them. Let's quickly write them out, and then I'll let you into your well-deserved break. Right, this is if we look at the next term here, and this in this case would mean that w at L would equal to w hat of 2. And what I'll do is I'll just write down the other two now, and we'll discuss them, what this means after the break. Right, because from our other two brackets that we've written down here, we have, this is also wrong, right, there's a minus sign here that I dropped, apologies, comma xx. Evaluated at 0 would be equal to m1 of y, of course, and then we have eiy w comma xx evaluated at L, and this would be equal to minus my2. And on the other side, right, this is maybe one thing, we have now a delta w comma x evaluated. Well, so we could say in principle this means then nothing else, but somehow this has to somehow be a Dirichlet boundary condition. And we did say w comma x was nothing else but our angle in our Euler-Bernoulli beam assumption, right? So we'll say w comma x at 0 would be nothing else but a rotation at this point, and w comma x at L will be a rotation at the other point. Now I'll let you go into your well-deserved break, and then we'll discuss what this means. For example, if you were to keep it flat, break, and then we'll discuss what this means. Means quarter past. All right, welcome back. Let's continue on our discussion over here. And the first thing we can do is quickly talk about what we're seeing over here. Namely, that we said, well, we have all of these funny terms of 3 derivatives in x over here equal to forces, and on this side we always have something, and we say this is actually a Dirichlet boundary condition. So let's write this down as is. So, and then we'll discuss why we all of a sudden have derivatives, which we now call Dirichlet boundary conditions. So here we have our natural boundary conditions, right, or Newman boundary condition. And what we have over here, and I'll tell you that these are Dirichlet boundary conditions. We'll discuss now why this is the case. And then this whole thing here together. Now I'm too short, I think, to close my box at the top. Don't want to fight with the board again. So all of this together, right? Our governing equation up here, plus our boundary conditions. This is nothing else but our strong form, right? This entire box out here. And the good news is, well, this we already said this makes sense. This is what you saw in mechanics too. This is indeed the governing equation for a beam. And now, if we take a look over here at our eiy comma xx, if you remember, if we want to compute a moment over here, we could take our sigma, which was nothing else but eiy comma x multiplied by z, and then we multiplied by z again to get the lever arm, and we would get at eiy comma xx as indeed a moment. I know I raised it from the board now, I apologize. And another thing that you might remember, hopefully maybe this rings a bell from your mechanics classes, when you take dm by dx, you would get a third derivative in x, and this would indeed be equated to a force. So our natural boundary conditions do indeed make sense. One question, why do we have different signs here? Do you remember where this comes from? Nobody remembers? If you're on the left or the right side of the beam, why you would have a different sign? Yeah, I heard some mumbling. Right, remember there was something as a positive cut and a negative cut on your beam, and depending whether you looked at it at either side, you would have a different sign convention, right? What was positive, what is negative. Do you remember that? Do I see some nods at least? Yeah, very good. Someone at least remembers. Yeah, actually, when I heard mechanics of solids many years ago, my professor was a very serious guy. But then he, in all his seriousness, stood there and said, well, just always think about whether it's a happy beam What's that be? And of course, the moments and forces are different on either side. So, but too stiff for me to bend, but really I thought you might enjoy this. But really, so whether we're positive or negative cut, you learned these things in class. So now, how come can we say that W comma X is an essential boundary condition? And let's write this right beneath here. Let's write this underneath here, because we somehow have to redefine what our Dirichlet boundary conditions are. So let's redefine. Because previously we always told you you always have to impose a deformation only as a Dirichlet boundary condition. So now we can say for our essential boundary conditions, right, essential Dirichlet is the same. We mean the same thing. So we now redefine and say an essential boundary condition, let me copy this down correctly, means we prescribe the primary field, this we're happy with, right, that's what we've been doing all along in the finite element course, the primary field, which here would be W of X, right, that was our primary unknown. And now comes the important part, and its derivative, or derivatives even, of lower order, it's a long sentence, lower order than the, let's write it, so then the, where do we go, the highest derivative appearing in the potential energy or the weak form. Long sentence, I mean. I can use my pointy stick. Give you a moment to finish copying down. So if we look at what this means over here, here we wrote down our potential energy, right? And here, this you see down here, this looks like our weak form, this first variation down here. And we see we have a second derivative in both. And we say that we define the derivative of lower order than the highest derivative appearing here. So that would be order 1, right? And this is why for beams we have the special case that we have W comma X, so first derivative also being an essential boundary condition. This is really something special about beams. You won't see, in this course you won't see this again, but essentially what this now means is we have the first two derivatives correspond to our essential Dirichlet boundary condition, and the second and third derivatives correspond to our forces and moments applied. And again, just to emphasize this, so we have an or sign here, right? At each point, just as we saw for the bars already, you either prescribe a force or you describe a displacement. The same goes here. You either prescribe a force or a displacement, or you prescribe a moment or a rotation. All right. Now let's recap again what our weak form was. So we will be using this later on. So maybe we can still do this on this board. I'll probably regret saying that. A little bit higher. Yay. One day I'll be able to operate this board as well. So remember now when we want to go forward and start defining a finite element, we'll go here and we define our weak form. And you remember something like this over here would be nothing else but our bilinear form, right? And all of these terms along the way down here, all of these would be our linear operators, right? So let's quickly write this down. Maybe even on a new board. I think that will make life easier. Then you can see this up there and I can write underneath. So we can use this up there, our first variation, to define our weak form, right? Our Galerkin weak form, you denoted that by G, which depends on W, delta W. And that is then nothing else but your bilinear operator, right? Which depends on W, delta W, minus your linear operator over here, which just depends on delta W. And maybe let's just write this out again over here. here, our B of W delta W is nothing else. Well, what we boxed up there, 0 to L of EIY over 2 multiplied by W comma XX delta comma XX delta W comma XX dx. Right, that's our bilinear form that we also highlighted there, and all the rest of this, all our F1s, M's, and so on, this is all our linear. This all falls under this operator over here. And then we can say, well, we're looking for a W in our function space U. So here we have W, which has to be in which order of H? What? Yes. If this is our bilinear form over here, right? So this is our bilinear form over here, so it has to be square integrable to second order, right? Because we'll need second derivatives over here, of course, over 0 to L. And here again, as I said just now, here we have to be careful that W will equal to W hat, the prescribed this deflection, and, or, depending what we do with our first derivatives, W comma X will equal to theta hat on our Dirichlet boundary conditions, on our essential boundary conditions, which we'll just denote as such. So now let's finally, after we've been going for quite some time, introduce our beam element. Let's do this right next door. So this you'll find then in chapter 12.4, and this is now the 2-node, because we've been doing all the groundwork now, the 2-node Euler-Bernoulli beam element, finally. Euler-Bernoulli beam element. Wow, long heading. So now I'll give you another thing that we need to recall. We saw it on the slides earlier on, and you saw it last week, that we could then also define our stiffness matrix, KAB, was nothing else but that we take our bilinear form that we have over here, and we plug in our shape functions, NA and NB. Right, and if we do this if we take our bilinear form and plug in NA here, NB here, we have our stiffness matrix. So let's do this. Now that we're starting to talk about beam elements, I'll integrate over the length of our beam element over here, and we have our EIY multiplied by NA comma XX and NB comma XX dx. So here, this was a question that also came up a few times. So this means when we need to have a second derivative has to exist for our shape function. So what we had for our bars, where we had a first derivative linear interpolation, this will no longer work, right? Because we would get 0 as our second derivative. So let's take a look. What could be our basis of interpolation? So our basis for interpolation. Right, that would be, so we have a constant linear term, right? It would at least have to be quadratic for us to be able to compute our stiffness over here. So let's write this out like this. And then let us go ahead and, which one was it? Okay. So now let us go ahead and define our 2-node beam element. So we say we wanted to have 2 nodes, and we wanted to be beam elements, so we say 2 nodes, node 1 over here, node 2 over here. And then we say we want to have our deflection over here, our W, which is our primary variable of this element, which depends on X. We say we want to use a quadratic interpolation base for it. So we would have something like C0 plus C1 of X plus C2 of X. And do you recall what you did for the bar elements, right? So we said we need some conditions to find these coefficients over here. Let's start with the first thing we could do, right? We could say, well, we have our WE, the deflection at node 1, and we might have the deflection at node 2. Just for consistency, again, X goes along the length over here, and let's say this is the length of our beam element over here. So what we could do is say, well, we know W of 0 is equal to W1E, W at L will be equal to WE2, right, the deflection at this node over here. But what would you suggest we do to find the next ones? Yes. Oh, yes, there's a square, of course. Thank you. This here is x. Oh, I got carried away. Sorry. It's the same x along the line. Sorry for that. Got carried away with my subscripts here. Good, you're listening, someone. So yeah, we of course have an x, right? Because this is really the coordinate along the length of our beam element. So we say we could use our two deflections over here as two conditions already, but now if we have a third coefficient, what would you suggest we do? Someone have an idea what you would do, how you would find the third coefficient? Any idea? It can be a wild idea. What would you do? You have an idea? Right? We could, for example, use a third boundary condition. Do you have anything to suggest? Exactly, our first derivative, right? We could, for example, go over here and say, well, how about we define our rotation over here, which is nothing else but a first derivative. Right? Now we have one more problem, though. Right now, okay, it's great. We define one rotation on one end of our beam. And actually, I think we typically, by convention, we define them this way around, sorry. Just to be consistent in what we're doing. But what this means is we still wouldn't be continuous in our rotations along the length of our beam. Right, so ideally what we want to do for this this beam element is very special. What we plan to do is say, well, why not take another boundary condition on this side, theta 2 hat. We say w comma x, L is theta 2 hat. Right, and then we add another coefficient into here, which is cubed. And this then takes into account for something very, very important, which is, well, that exactly our node. At our nodes, both the rotations and the displacements are defined and are the same. So if you have another element on this side here, it will have the same rotation because it shares the same node. Hence, you'll have a nice and smooth function and not something that might look like this at a node between two elements. But rather, if the angle here is the same, which is nothing else but the derivative here, you would have a nice and smooth function at this point. Right, and this is what we want to do. So last bit we want to do today is figure out how this then will look like, how our shape functions will exactly look like. And we can stay down here for that. So we say this sounds great, that we're using a cubic polynomial for it, with these four boundary conditions, which also makes sense, right? Because we said we have two deflections, two rotations that are essential boundary conditions that we could enforce. So our approximate solution will look something like this now. Right, we have W, E, H, right? Because H just means we're approximating our continuous field over here. Will be something like, for our first coefficient here, we use the displacement at node 1, and we multiply it by a shape function now at node 1, belonging to node 1, shape function 1, plus we have W2 with the shape function. All right, because this satisfies our first equation, then we just have WE1 N1 plus WE2 N2 on our end points. But then if we want to impose theta over here, what we have to do is and NB. And do you recall what you did for the bar elements, right? So we said we need some conditions to find these coefficients over here. Let's start with the first thing we could do, right? We could say, well, we have our WE, the deflection at node 1, and we might have the deflection at node 2. Just for consistency, again, x goes along the length over here, and let's say this is the length of our beam element over here. So what we could do is say, well, we know W of 0 is equal to W1E, W at L will be equal to WE2, right? The deflection at this node over here. But what would you suggest we do to find the next ones? Yes. Oh, yes, there's a square, of course, thank you. This here is x. Oh. I got carried away, sorry. It's the same x along the line, sorry for that. Got carried away with my subscripts here. Good, you're listening, someone. So this is really the coordinate along the length of our beam element. So we say we could use our two deflections over here as two conditions already, but now if we have a third coefficient, what would you suggest we do? Someone have an idea what you would do, how you would find the third coefficient? Any idea? It can be a wild idea. What would you do? You have an idea? Right? We could, for example, use a third boundary condition. Do you have anything to suggest? Exactly, our first derivative, right? We could, for example, go over here and say, well, how about we define our rotation over here, which is nothing else but a first derivative. Right? Now we have one more problem though. Right now, okay, it's great. We define one rotation on one end of our beam. And actually, I think we typically, by convention, we define them this way around, sorry, just to be consistent in what we're doing. But what this means is we still wouldn't be continuous in our rotations along the length of our beam. Right, so ideally what we want to do for this this beam element is very special. What we plan to do is say, well, why not take another boundary condition on this side, theta 2 hat. We say w comma x, L is theta 2 hat. Right, and then we add another coefficient into here, which is cubed. And this then takes into account for something very, very important, which is, well, that exactly at our nodes, both the rotations and the displacements are defined and are the same. So if you have another element on this side here, it will have the same rotation because it shares the same node. Hence, you'll have a nice and smooth function and not something that might look like this at a node between two elements. But rather, if the angle here is the same, which is nothing else but the derivative here, you would have a nice and smooth function at this point. Right, and this is what we want to do. So last bit we want to do today is figure out how this then will look like, how our shape functions will exactly look like. And we can stay down here for that. So we say this sounds great, that we're using a cubic polynomial for it, with these 4 boundary conditions, which also makes sense, right? Because we said we have 2 deflections, 2 rotations, that are essential boundary conditions that we could enforce. So our approximate solution will look something like this now. Right, we have WE H, right? Because this H just means we're approximating our continuous field over here. Will be something like, for our first coefficient here, we use the displacement at node 1, and we multiply it by a shape function now at node 1, belonging to node 1, shape function 1, plus we have W2 with the shape function at node 2 of this element, plus we have theta hat 1 of our element, and now I'll do something special. I'll call this guy an M. See, this is another shape function, and we'll see in a moment why we give it a different name. Plus, then we have theta 2e, and we'll call this again ME2 of x, where we say all of these guys here are our shape functions. And we say that they are of quadratic order, right? Somehow so that we can satisfy those 4 boundary conditions. Similarly to what you saw in the bar element on the other day, just that unlike having just this and this, we have all 4 deflections over here. And this might still look a bit confusing to you now. Let's start looking at how these shape functions could look like so that they satisfy those conditions we placed over here. So let's plot once over here for x.